in the 1950s to counter the Soviet jet bombers at that time, or the threat of long-range anti-ship missiles launched by submarines. The U.S. Navy seeks a long-range, sea-resistant interceptor aircraft to defend carrier battle groups. Then Secretary of Defense Robert McNamara asked the Navy to pass TFX program with the Air Force, develop needed fighter aircraft. To save research and development costs, TFX derived naval version of the F-111B. It was originally responsible for General Dynamics and Grumman, but F-111B is seriously overweight. The performance also does not have the close combat capability required by the Navy. Grumman continued to modify it. In 1966, the Navy awarded a research contract to Grumman. Grumman selected design number 303 among multiple designs. During the same period, because the F-111B performance was insufficient and there was no solution, Congress terminates funding for F-111B and approves Navy development of replacement aircraft. In 1967, Grumman proposed an improved 303 design to the Navy for research. In 1968, the Navy proposed the VFX plan. In January 1969, the Navy selected Grumman's design. Grumman's original design was to use the F-111B's TF-30 engine. The Navy planned to switch to the Pratt & Whitney F-401-400 engine that was under development at that time. Because it has to carry 6 AIM-5 for Phoenix missiles originally designed for the F-111B, a WG-9 radar and 7,300 kilograms of fuel, even lighter than the F-111B. The F-14 is still among the fighters that can take off and land on aircraft carriers, the heaviest and largest model. In order to save time, the development skipped the prototype stage. Directly manufacture actual machines. December 21, 1970, just 22 months after the contract was awarded, F-14 first test flight. In early April 1972, the F-14 tested the AIM-5 for Phoenix missile for the first time. A single AIM-5 for Phoenix missile was launched in April 1973, hit a target 200 kilometers away. On November 22nd, an F-14 flew at Mach 0.78 at an altitude of 7,600 meters. 6 AIM-5 for Phoenix missiles were launched in 38 seconds. 4 of them hit the target directly, reaching initial combat capability in the same year. In the immediate period, due to its lightweight and compact size, solid-state electronic devices that are more reliable and better resistant to electrical warfare are developing rapidly. F-14 weapons continue to improve. Some F-14s switched to new engines F-110-400 in 1987. These F-14s were originally called F-14A+ and were renamed F-14B in 1991. The F-14D developed during the same period also uses the same new engine and has new avionics systems, includes glass cabin and Link 16 encrypted data link, and can improve the performance in high angle of attack and entanglement maneuvers. Flight Control Quality Digital Flight Control System, DFCS, in response to the Soviet Union's long-range bombers, long-range anti-ship missiles launched by fighter planes and submarines, threat to U.S. aircraft battle groups. The U.S. Navy's demand positioning for F-14, for air superiority fighters and naval long-range interceptors. Rigorous design requirements, including the ability to use the AIM-50 for Phoenix missile, a large and heavy long-range air-to-air missile to deal with saturation attacks. But at the same time, it must be able to maintain good mobility. Top speed must be as high as Mach 2.4, and the range depends solely on the built-in fuel capacity. It is also enough to give it a combat radius of 500 miles. High speed but long range. That is to say, low aerodynamic and low resistance must be maintained at high and low speeds. This means that a high lift-to-drag ratio is required at both high and low speeds. To meet this requirement, the F-14 uses variable sweep wings. There are also 2 advantages, including providing sufficient lift under high load and low airspeed conditions when the aircraft is ascending and descending, Keeping aerodynamic drag as low as possible throughout the entire flight envelope also benefits maneuverability, especially the ability to continuously turn. But using variable sweep wings will increase weight. Each Phoenix missile weighs 460 kilograms. The F-14 can carry 6 pieces at the same time, which is 2,760 kilograms. Under this load, the Navy also requires the F-14 to have good maneuverability. To this end, the F-14 is designed to place the two engines in separate cabins on the left and right sides of the fuselage, and quite a distance apart. A flat body is formed between the two engines. It is gradually thinned from the cockpit to the rear to form a lifting body. Produces up to 40 to 60% lift depending on wing sweep angle. This makes the F-14 with variable sweep wings. Its wing load is only 215 kilograms per square meter to 230 kilograms per square meter, which is surprisingly low. The wing covers are outside the two engines. The wing shaft is deliberately chosen to be at the outermost part of the wing cover. This makes the F-14's wing axis spacing larger than that of many variable sweep wing fighters of similar size. This not only reduces the sweep time of the variable sweep wing, but also reduces the problem of the lift center of gravity moving backward, improved resistance at high speeds. At the same time, there are additional racks under the wing covers to accommodate weapons. Plus, between the two engines, there is quite a lot of space under the fuselage that can be used to mount weapons. The F-14 has plenty of room to mount weapons. No need to install fairly complex weapons racks in the wings to give the driver a good view. Its cockpit cover is a bubble cover design. The cannon is a 20mm M6A1 Vulcan cannon placed on the left side. The F-14 fuselage has a 3-trunk fuselage structure. The two engines are placed in separate cabins behind both sides of the cockpit, a few inches away from the cockpit. The cockpit is tapered towards the rear. A flat fuselage between the two engines connect the two engines. This section of the fuselage houses the fuel tank, electronics, flight control systems, and mechanical structure of variable sweep wings. This aerodynamic layout is compared to placing the engine nozzles closely together. Have lower aerodynamic resistance. Because the two nozzles are too close, the airflow will interfere with each other. The flat fuselage also becomes a lifting body other than the wings. Bring extra lift to fighter planes. Reduced wing loading. Greatly improved steering ability. The Su-27 series of the former Soviet Union also used a similar design. F-14 wing sweep angle can vary from 20 fully extended to 68. Maximum change speed is 7 degrees per second. The sweep angle is determined by the flight computer on board. Central Air Data Computer, CADC automatic control. It can also be directly controlled by the pilot if necessary, allowing the wing to fly at any altitude and speed. Can achieve the best lift-drag ratio. This gives the F-14 amazing high speed and turning performance. When parked, the wing sweep angle can be increased to 75. Partially overlaps the horizontal tail elevator to save valuable space on the aircraft carrier. In case of emergency, wing sweep angles of 68 or asymmetrical can also be used to lift and land on aircraft carriers. The 3-trunk body reduces aerodynamic resistance. Variable swept wings optimize lift-to-drag ratio in any environment. In addition, the flat body generates considerable additional lift, especially when the main wing is retracted to the maximum sweep angle. More than 60% of the lift is generated by the fuselage. F-14 horizontal tail can be differential or linked between +15 and -35, responsible for controlling lift and acting as ailerons together with spoilers. When the main wing sweep angle is less than 50, roll is caused by the spoiler and horizontal tail. When it is greater than 50, the horizontal tail is responsible. The original design of the F-14 had only one vertical tail, compared with a single vertical tail. Twin vertical stabilizers can maintain the same maneuverability, have lower height, more suitable for aircraft operating environment. Since the wing sweep angle is variable, the underwing pylons cannot be fixedly mounted under the wing. Otherwise, the pointing of the weapon cannot be consistent with the pointing of the nose of the aircraft. If the rack is to be mounted and then the sweep angle changes, the corresponding adjustments should be made. It becomes mechanically complicated. Weight, reliability, and cost all have an impact. Fortunately, the F-14's flat fuselage and wing covers provide sufficient space for weapon racks. Grumman then moved all the pylons. Both are installed on the flat body and wing covers. The basic weapon is built into the left side of the fuselage. A 20mm caliber M61A1 Vulcan cannon under the cockpit. F-14 shell supply system. What is slightly different from other fighters is that used cartridge cases will be returned, will not be emitted outside the aircraft. The reason is that the cannon is located in front of the air intake. Abandoned cartridge cases may be inhaled and damage the engine. Equipped with 676 rounds of ammunition, the underwing pylons need to rotate in response to changes in the angle of the wing. So the F-14 has no pylons on its wings. Weapon racks are placed in multiple places on the fuselage. Flat bottom of the fuselage, belly position. There are 4 weapon racks in the front and rear rows. Bombs, air-to-air missiles, jamming and reconnaissance pods, etc. can be carried here. There is also a weapons rack under both wings. Can carry to air-to-air missiles using twin pylons, a missile and a rocket capsule, or a missile and low-altitude night calibration and navigation pod lantern. When the F-14 carries 6 AIM-5 for Phoenix missiles. However, the space between the ground and the ground was too small and the position of the wing cover was changed. Weapons that can be mounted include the AIM-5 for Phoenix long-range air-to-air missile, AIM-7 Sparrow semi-active radar-guided medium-range air-to-air missile, AIM-9 Sidewinder infrared homing short-range air-to-air missile. Due to the retirement of the A-6 and no successor aircraft, the F-14 was assigned a ground attack role in the 1990s. But because the main mission of the F-14 is fleet protection, other fighters are responsible for the ground attack. Initially, the F-14s used unguided bombs. Later, in order to be able to use precision-guided weapons, the F-14 is equipped with a low-altitude navigation and nighttime infrared calibration cabin. Give the F-14 a forward-looking infrared system, night combat and laser target calibration capabilities. Other weapons and equipment. In the early days, the F-14 could only carry various air-to-air missiles. After modification, it can carry bombs, rockets, reconnaissance pods, electronic jamming systems, and more. F-14 options on fixed wing covers. Set one mount point on the left and one on the left. (1990s). The ultimate model of the F-14, the F-14D, enters service. The F-14D uses the same GF1102-400 engine as the F-14B. It is also equipped with the Digital Flight Control System DFCS. The F-14 Tomcat is finally getting old. With the increase in maintenance costs and the aging of the machine body, Navy has to start retiring Tomcats. The end of the Cold War, it also makes the Tomcat-S job. Fleet air defense becomes less important. September 22, 2006, retirement ceremony for the last Tomcat, held at Naval Air Station Oceana. Analysis of U.S. military power. Thank you for watching. Goodbye.